All right, let's jump right in. We need to talk about a threat that's basically flipping the script on AI security. It's called model denial of service. And no, this isn't your classic network flood. This is a targeted, surgical strike aimed right at the computational heart of your AI.
Look, as engineers, we've all put in the hours hardening our networks against DDoS. We know that playbook inside and out. But what happens when the attack just sidesteps all of that? What happens when it ignores the network completely and goes straight for your model's compute? That's the question we have to answer.
And this is the fundamental shift right here. Traditional DOS, that's a brute force game. It's all about overwhelming bandwidth, measured in gigabits per second. Model DOS, it's a completely different beast. It's a strategic attack on your CPU and GPU, measured in how much it costs you to process a single request. And here's the kicker. An attacker with a tiny amount of bandwidth can now cause an insane amount of computational and financial damage. The whole game has been turned upside down.
So how in the world does an attacker actually do this? How do they weaponize your own model to bring you down? Let's get into the anatomy of how these compute attacks really work. First things first, you got to understand how they get in. What are the specific vectors an attacker is looking for to exploit your model's computational core? The most direct way is something called resource exhaustion. Now, this isn't about sending junk data. It's way more clever. It's about sending what looks like a legitimate request, but it's been specifically crafted to trigger your model's absolute worst-case performance. Think about asking an LLM for a 10,000-word story where every single sentence has to be a palindrome. It forces the model down an incredibly complex and inefficient path, torching your GPUs on a single malicious query.
And that leads to something even more precise: algorithmic complexity attacks. Now, for us as engineers, this is where it gets really scary and kind of interesting. This isn't just about making the model work hard. It's about exploiting its fundamental architecture. A perfect example: someone targeting the O of n squared complexity of a transformer's attention mechanism. An attacker who knows what they're doing can feed your LLM a crazy long input sequence, knowing full well it will trigger a quadratic, not linear explosion in compute, grinding your whole system to a halt. They're weaponizing big O notation against us.
Which all leads to the ultimate business nightmare: economic denial of sustainability, or EDoS. With these attacks, the goal isn't just to cause downtime, it's to literally bankrupt the service. The attacker sends just enough of these heavy-duty queries to kick your cloud's autoscaling into high gear. And suddenly, that feature we all rely on to stay resilient becomes a weapon pointed right back at us, spinning up more and more expensive GPUs and leaving you with a cloud bill that is just catastrophic. And just to put that financial risk into perspective, think about this number: $270,000. That's what a typical DDoS attack costs, on average. Now imagine an EDoS attack targeting a fleet of high-end GPUs. You could blow past that number in a matter of hours, not days. The financial exposure here is just immense.
Okay, so with all these threats out there, you're probably asking yourself, is my model a target? Well, not all AI systems have the same risk profile. Let's break down the hierarchy of vulnerability. This table lays it out pretty clearly. Right at the top, with a high vulnerability rating, are large language models. And it makes sense why, right? First, they have this unbounded natural language input space, which makes it almost impossible to validate every malicious query. And second, there's that quadratic complexity we just talked about. Computer vision is in the middle. Adversarial examples can be crafted to max out latency. And then you have recommendation engines, which are a bit lower risk, but they're still not immune. So who's actually getting hit? Take a look at this. The biggest piece of the pie at 36% is software and computer services. Yeah, us. So the key takeaway here is that the very industry building and deploying these incredible AI models is also the #1 target. This is not some far-off hypothetical problem. It's happening to our peers right now. Okay, enough of the doom and gloom. We've defined the problem. Now let's talk about solutions. As engineers, how do we actually build resilient systems? We need a solid, structured framework for defense. The strategy really comes down to defense in depth. It's built on 4 key pillars. You start with a secure architecture, then you add application controls at the perimeter, then you harden the model runtime itself, and you wrap it all in good operational practices. You can't skip a layer, you need all 4. So architecturally, this means thinking about security before you've even written a line of code. It means doing threat modeling and asking, how could someone abuse this?
It means shrinking your attack surface by putting models behind API gateways, getting rid of single points of failure, and using well-known patterns like the circuit breaker to make sure one bad component doesn't cascade and take down the entire system.
At the application gateway level, this is your first line of defense. It's your filter. And honestly, the single most critical control here is strict input validation and sanitization. Period. If an input doesn't match the length, format, or type you expect, you just drop it, no questions asked. Back that up with solid rate limiting for each user and IP, and a web application firewall that has custom rules designed to spot the fingerprints of a computer attack.
And finally, we get right to the model itself. At runtime, hardening is all about direct resource management. We're talking hard limits on your task queues so a backlog can't just eat all your memory. More advanced setups can even do a quick computational cost analysis to pre-screen and reject queries that look suspiciously expensive. And critically, you need a plan for graceful degradation. If your main model is getting hammered, have a smaller, simpler fallback model ready to go.
So what's next? Where is all this going? Well, we're basically entering a new phase. It's an AI-powered arms race between the attackers and the defenders.
The future here is pretty clear. The attackers are going to use AI to find vulnerabilities automatically and launch adaptive attacks that change tactics on the fly. So, in response, our defenses have to get just as smart. We're talking about AI-powered WAFs that actually learn what normal traffic looks like and automated response systems that can deploy countermeasures in seconds, way faster than any human ever could.
And a huge part of this future defense is going to be transparency. We're going to see the rise of the AI bill of materials, or the AI bomb. It's just like an S-bomb for software. It'll be an inventory of everything that went into your model, the foundational models you built on, the datasets you used, the fine-tuning libraries. This is going to be absolutely essential for managing the massive supply chain risks that we all inherit when we use transfer learning.
So I'll just leave you with this final thought. For years, we've treated inference costs as a key performance metric, something to be optimized and pushed down. But it's time we start asking a new question. Is that cost just another line item on your performance report, or is it actually your model's biggest security vulnerability?